This is a capacitor tutorial presented by DB. Hello, welcome to a new tutorial presented by DB. In this tutorial, we're going to see capacitors. As an introduction, we need to know that capacitors are circuit elements which are used to store charges when they are visualized in DC circuits or direct current circuits. The function of capacitors in alternating current is going to be varied because the capacitors are going to act as resistances, where the resistances are going to be called reactance of capacitors. But here, the capacitors are going to, in direct current, capacitors are going to act to store charges, electric energy, and has electric field. The capacitor consists of two conducting plates which is separated by a dielectric material. The dielectric material can either be air, ceramic, paper. So now the following are the use of capacitor. We have number one, storing charges, and it has voltage and store voltage in appliances. Number two, it can be used to tuning circuit in radio receivers, and when it's used in tuning circuit in radio receivers, this is in case of alternating current, and in this case they are used as reactances, and they can be used as dynamic memory element in computers. Now, action of capacitors. Let's visualize the action of capacitors. This is the case where you have a circuit. So in this circuit, when you connect capacitors, what's going to happen is that these positive charges are going to cause the electrons which are found on this plate to move here as such here. So all the electrons are going to move in this position here, and thus they are going to cause this plate A to be negatively charged. And the electrons which are found here are going to move on this other plate and cause this plate to be positively charged. These are going to correspondingly cause positive charge here and negative charge here on the dielectric material. So this is how a capacitor is. A capacitor consists of two plates with dielectric material which is situated inside here. So this is the conducting plate here, and this conducting plate is going to be negative charge to the movement of electron here, and it's going to be positive charge to the movement of electron out of the plate A. So this is the action of capacitors. So now let's write some definition of terms. So with definition of terms, you have capacitance. Capacitance is the ability of capacitor to charge transfer for a given amount of voltage. So the ability of a capacitor to store electric charges for a given amount of voltage said to be the capacitance, and this is equals to Q all over V. Now, capacitance of 1 farad, this is the ability of capacitor to store 1 coulomb of electric charge for 1 volt of potential difference existing between the capacitor. So 1 coulomb all over 1 volt is going to be equal to 1 farad, and the capacitance is going to be measured in farads. Now let's realize the factor affecting the capacitance of capacitor. There are 3 main factors affecting the capacitance of capacitor. We have number 1 factor which can be separated into other factors, which number 1, the physical dimension of the capacitor. The physical dimension of the capacitor, e.g. the area and the radius. So we have the physical dimension of 1 capacitor plate. So the area of this capacitor of 1 capacitor plate can be used in order to affect the capacitance of the capacitor. Number 2, we have the spacing between the plate. The spacing between the plate here is characterized by D. So we first have the area of each capacitor plate. We have the spacing between the plate D. The second factor affecting it, we have the dielectric material. Dielectric material here. The dielectric material is going to cause a change in in the permittivity. So E here, epsilon. So now the dielectric material has a degree of polarity alpha which affect the the epsilon area, and thus epsilon. And now the formula which links the relative permittivity to the factor of the dielectric material we call the degree of polarity is going to be relative permittivity equals to 1 all over 1 minus the the degree of polarity here. This is a relative permittivity. And now the formula of capacitance is given by C is equals to epsilon A all over D, where epsilon is equals to epsilon R times epsilon 0, and we have visualized it initially in the chapter of electric field. Now this is in the case of a parallel plate capacitor. With a parallel plate capacitor, you have two plates which are parallel to each other, separated by a distance d. And with this parallel plate capacitor, the capacitance is epsilon A, the distance of each plate, the area of each plate, divided by the distance separating the plate, and epsilon is a permittivity of the medium, and the medium here is due to the dielectric material. And the dielectric material is going to produce what? The degree of polarity, and the degree of polarity is going to affect the epsilon R, or the relative permittivity, which is going to affect the epsilon, or the permittivity of the medium. Permittivity of the medium is equals to epsilon R times epsilon 0. So all this formula is going to be equals to epsilon 0 all over 1 minus degree of polarity. Now, in case of spherical capacitors, we note that the capacitance is going to be 4 pi epsilon R, where here epsilon R times, where epsilon is equals to epsilon R times epsilon 0. So now let's have the proof. So now let's prove for this formula above here for capacitance equals to 4 pi epsilon R. So now from our concept from the chapter of electric field, we know that V voltage is equals to Q all over 4 pi epsilon R. So this is a formula for the electric potential that we had in electric field. And we also know that the electric potential is also going we also know that the capacitance that we visualize in this chapter is equals to the charge per unit voltage. So this was the formula of V inside electric potential inside the electric field we initially had. Now when we want to prove for the formula of C is equals to epsilon A all over D, we note that V is equals to Q all over 4 pi epsilon R. So if I multiply if I multiply times R, also the numerator by R, I'll multiply the denominator by R. So I'm going to have Q all over 4 pi R squared epsilon times R. So 4 pi R squared is similar to be the area, and R here is similar to be the distance. So V is going to be equals to QR all over A epsilon. So now this R here is going to be considered as a distance. So but we know that C is equals to QR all over V. So now the C here is going to be, I divide Q all over this V here, I substitute in this equation. When I substitute, I'm going to have Q times epsilon A all over QD. So now I place this value, I can multiply here. So I see that C with the capacitance is equals to epsilon A all over D, where epsilon is equals to epsilon R times epsilon 0. And this is the initial formula we have for parallel plate capacitors. Now let's prove for the formula C is equals to 4 pi epsilon R in cases of circular plate capacitors. In case of circular plate capacitors, we know that V is equals, still know that V in electric field is equals to Q all over 4 pi epsilon R. But in this chapter, we realize that the capacitance, the ability for a capacitor to store charge per unit potential difference, which is placed across it, V. So our C is equals, so I substitute this value of V inside. So Q all over 4 pi epsilon 0. When I do that, I multiply here. So my C capacitance is equal to 4 pi epsilon R, where epsilon is equals to the relative permittivity times the permittivity of free space. So now this formula above here, these two formula above here, were the formula when the dielectric material, in these cases here, the dielectric material occupy the whole space between the capacitor plate. When the dielectric material occupy the whole space between the capacitor plate, we have this formula here. Now, if the dielectric material does not occupy the whole space, we are going to have the modification of the formula of dielectric material due to dielectric spacing. So now let's say that the dielectric material occupies a space T and the whole distance between the plate is going to be D. So we initially know that the first formula for when you are going to have the whole dielectric material, so C is equals to epsilon 0 A all over D. And we also know that C is equals to Q all over V. Electric field strength is equals to V all over D. We know that from electric field, and V is equals to E times D, so found from this formula. We also know that electric field strength in electric field is equals to the charge density divided by the permittivity of the material. So V is going to be equals to charge density times D divided by permittivity of the material. So now when visualizing back this diagram, we visualize that the thickness T here, the dielectric material occupies a space T, and the space which is not occupied by dielectric material is going to be D minus T, and that D minus T is going to be a space where you are going to have a permittivity of free space being equals to the permittivity of the medium being equals to the permittivity of free space. But in this thickness T, you are going to have the permittivity of medium being equals to the permittivity of the dielectric material. So now we are going to summarize this diagram above with this equation here. We will say that the voltage V1 is going to be the voltage produced by the dielectric material, so this voltage across here, plus the voltage produced by the vacuum / air, or with the space without the dielectric material. So you are going to have VT, which is with the dielectric material, plus VDT, which is without the dielectric material. So here is going to be E0, so it's small confusion at this position here. We're going to have E0 at this position here and E here. So it is this all over epsilon and this charge density all over epsilon 0 times D minus T. So upon continuing the solution, you are going to end up with this answer as being the modification of, we are going to have now the V being equals to this. Now since you find for the value of V, we need to know that V0 is equals to V divided by dt, so V times D all this. So now when you have all this, you know to know that the by simple proportion, C1 all over C0 is equals to V0 all over V1. When you have all this, we are going to substitute now back into this equation, and the final answer for the capacitance is equals to epsilon A all over epsilon out T plus D minus T. Now let's visualize now the energy stored inside the capacitor. The energy stored inside the capacitor can be found with three formulae. We have number one, the first formula is when the voltage varies, the second formula is when the charge varies, and the third formula is when the voltage and the charge varies together. Now in the first case, when the voltage varies, let's visualize when the voltage varies. So when the voltage varies, we need to know that from what is the definition, from the definition of voltage, we need to know that voltage is defined as, from definition of voltage is defined as the work done is voltage defined as the work done per unit charge, as we have seen inside electric field. The work done, voltage is defined as the work done per unit charge, so it implies that the work done will be equals to the charge times the voltage. So now, see, if there is a change in the work done, it implies that there's going to be a change in the charge, in the change in the voltage. So provided that the voltage varies and not the charge varies, so the change in the work done is going to be due to a change in the voltage. So now dW is going to be equal to Q dV. So now we know that at time t equals to 0, the energy is going to be 0 joule and the voltage is going to be 0 voltage. So if in this circuit, when you connect the capacitor to the battery here or the cell here, we realize that at the start, when the time is 0, the energy stored is going to be 0 and the voltage across the capacitor is going to also be 0. Inside the capacitor is going to be 0. So we are going to put it as limit here. So the integral from the start 0 joules here to an energy of E here is equals to integral from 0 of voltage 0 here to a voltage V here. So now we know that, but Q is equals to C times V. Since Q is equals to C times V, we can substitute here, and we are going to have the integral of that, integral of 0 V CV. So when we integrate, we are going to have the work done with the limit 0 and A is equals to half CV squared with the limit V and 0. So the energy when the voltage varies is given as half CV squared. So now, in case when the charge varies, you still have the same formula, W is equals to QV, but now in this case here, the change in the work done is going to be due to a change in the charge, because here the charge varies with respect to time. So now dW here is going to be equals to V dQ. So at the time t is equals to 0, the energy is going to be 0 joules and the charge is going to be 0 joule on the capacitor. And at the time t is equals to t, the energy is equals to E. So it starts from 0 here to E, and here the charge starts here from 0 to Q. So but V is equals to Q all over C, and we are going to substitute here in this formula. When you substitute the final formula upon integration, you are going to have E is equals to Q squared all over 2C. So this is the final formula for the energy stored when the charge varies. Now, in case when the charge and the voltage varies, we are going to have dW here is equals to dQ all over dV, and the final formula is going to be QV. But this final formula QV is the total energy of the capacitor. The total energy of the capacitor QV is this QV is the total energy of the capacitor, but when an exam you are asked to find for the energy of capacitor, it must always contain a half, because some energy is released from the capacitor. So the half of this energy is going to be released on the capacitor. Normally, QV is going to be the total energy on the capacitor, but when you're asked to find for the energy of capacitor, the energy stored inside the capacitor, only half of that total energy is going to be stored, because the other half is going to be released from the circuit, and this other half is going to be due to the resistance of the circuit and the internal resistance of the capacitor. And number 2 is going to be due to the electric rays are lost. Electromagnetic waves are lost upon storage of charges. These are the two main reasons which make the energy stored to be only half QV. So from here we see that when the voltage and the charge varies, the energy varies together. The energy is going to be given as energy stored is going to be given as half QV. But the total energy of the capacitor, when you don't omit the loss of energy from resistance of the circuit and the emission of electromagnetic waves, it is going to be QV, or it's going to be CV squared, or it's going to be Q squared all over C. So now let's visualize now connection of capacitors. So now if capacitors are connected as such here, so this is a parallel connection of capacitors and this is a series connection of capacitors. So in a parallel connection of capacitor, you can connect it like pole connection and unlike pole connection. And like in this case, here you are going to have a like pole connection. This plus is going to be connected to this plus, this minus is going to be connected to this minus. This is unlike pole connection, this minus connected to this plus and this plus connected to this minus. Now in this case, in the like pole connection, we see that the sum of the charges is Q plus Q. The positives are going to sum up and the negatives are going to sum up. So you have total Q is going to be equal to Q1 plus Q2. Now voltage, we know that voltage to find the voltage, you say that from Q is equals to Q1 plus Q2 and Q is equals to CV. So you know that this Q is going to be C times the total voltage which is going to be produced. This Q1 is going to be C1 times V1, and this Q2 is going to be C2 times V2. Now we know that this C, total C, is going to be the total capacitance which is going to be produced due to the parallel connection of these capacitors. We know that the parallel connection of capacitors is going to be like a series connection of resistors. So now this total C is going to be equals to C1 plus C2. So you are going to first have V is equals to C1 plus C1V plus C2V2 all over C. But this C here is the parallel connection. So we have a parallel connection of capacitors. But this parallel connection of capacitor is similar to a series connection of resistors. So C is equals to C1 plus C2. When you are going to divide, you are going to have this. So V, the voltage across those capacitors connected, like pole capacitors and parallel capacitor connection, we are going to have C1 V1 plus C2 V2 all over C1 plus C2. Now the energy stored, we need to know that energy is equals to Q2 all over 2C. So but Q is equals to Q1 plus Q2, and C, the total C is equals to C1 plus C2 in this case. So we are going to have this Q1 plus Q2 all over C1 plus C2 all into squared here, because this is the value of Q. So when we substitute down, we know that Q1 is going to C1 V1 and Q2 is going to be equals to C2 V2. So the total energy in the circle is going to be C1 V1 plus C2 V2 all squared divided by C1 plus C2. So this is the energy of capacitor. And please don't forget a 2. So the 2 has been omitted here. So it is going to be half. There's half here. So unlike pole parallel connection, unlike pole parallel connection here, we have charge. Now the charge here on an unlike pole parallel connection, in this case, we have a minus connected to this plus. So we see that there is an opposition in this case. Since there is an opposition, the total charge Q here is going to be equals to Q1 minus Q2. Now the voltage, we are going to have Q is equals to Q1 minus Q2, and this Q is also going to be equal to CV. So CV is going to be equal to C1 V1 minus C2 V2. So now when you take this formula, divide again by C, so voltage is going to be equal to C1 V1 minus C2 V2. But we know that for parallel connection of capacitors, the total capacitance is going to be equal to C1 plus C2. So voltage is going to be equal to C1 V1 minus C2 V2 all over C1 plus C2. And so the energy stored is also going to be the same as what was found, but the only difference that with the unlike pole parallel capacitor has is with a negative sign here. So we are going to have a negative sign here, and please don't forget the half. The half is omitted in this case because the energy stored is always half of the total energy. Now we have a series connection of capacitors. So the series connection of capacitor can be separated into like pole series connection, and we have unlike pole series connection. In this case, this is a like pole series connection because the plus side is here and the minus side is here, and this is the unlike pole series connection here. So when you are connecting the positive here, negative here, positive here, negative here, this is the like pole series connection, this is the unlike pole series connection. Now with the like pole series connection, you see that here the voltage is not going, here the voltage is going to be a summation of the voltages since they are in series. So V is going to be equal to V1 plus V2. So since they're in series, the voltage is going to be a sum of the two voltage. V is equal to V1 plus V2. So now the charge is going to be from V is equal to V1 plus V2 and V is equal to Q all over C. We know that this V is going to be a Q all over the total capacitance, and this V1 is going to be a Q1 all over C1. This V2 is going to be a Q2 all over C2. So now in order for us to find for the Q, the total charge now which is going to be produced, we are going to multiply times C here. But C in this case, we are going to multiply times C, so we are going to have cure 1 all over C plus cure 2 all over C times C here. Now, but this C here is equals to C1 C2 all over C1 plus C2, because now here we need to know that in a series connection of capacitors, this is similar to a parallel connection of resistors. So the total capacitance is going to be C1 C2 all over C1 plus C2. So when you have this, you are going to have Q is equals to C1 C2 all over C1 plus C2 times this part here, because when there is a change, you change it, you're going to have C1 C2 here at the denominator. You're going to have C2 Q1 plus C1 Q2 here. So when you have this, you're going to say that Q, you multiply times this other part here. So this is going to cancel here, and this is going to stay in the denominator. So Q is going to be equal to C2 Q1 plus C1 Q2 all over C1 plus C2. So this is the charge which is going to be produced. Now the energy stored is going to be equal to E all over Q squared all over 2C. Now we know that need to know that Q is equal to C2 Q1 plus C1 Q2 all over C1 plus C2, and this C is equal to the total capacitance of the circuit. Now since in a series connection, we are going to have C1 C2 all over C1 plus C2. So now when putting it here with the half, we are going to see that energy is going to be equal to this here, which is the Q, is going to be the Q here all squared. The squared has been forgotten, please. So it's going to be the Q all squared times C1 all over C, or 1 all over the C, which is C1 plus C2 all over C1 C2. So when you do that multiplication, you are going to have the C1 and C2 here. So this formula is not actually correct because here was a squared here. So now let's visualize the unlike pole connection. With the unlike pole connection, the difference is that they are only going to be a minus sign at each of the formulas that we are going to have here. So that's the difference with unlike pole connection. So from here we have seen all the different sections which are involved with capacitors. The other part of capacitors which is involved with the connection with the resistors and a cell is going to be visualized in direct current circuit. So from here, I say thanks for your attention, and please don't forget to like and subscribe for Science Dream Makers. Thank you.